Thanks for the invite and thanks for having me. Oh, there's something in the chat on Zoom already. Oh, nothing important. That's fine. Okay, so I'm going to be talking about volcano deformation. That's where the majority of my research lies. And I'm going to be focusing primarily on the case of Soufrière Hills Volcano in Montserrat. And what I'm actually going to do is, rather than talk about one sort of study or project in detail and spend 45 minutes on one project and then probably bore you to death with the details that you probably don't care about so much, I'm going to briefly go over 3 different projects, focusing mainly on the big picture results rather than all the nitty-gritty. And come on, good. And the big thing I wanted to highlight, this is very much a team-led project. So while I'm here, the one delivering the talk, I'm going to be picking on results that have been developed by all this team of people that you can see here. And none of this work would be at all possible without the work done by the Montserrat Volcano Observatory. So they're the guys out there collecting the deformation data that we're using to sort of validate our models and our results. So before I get into the sort of projects we're going to be talking about, I was going to give a little refresher on volcano deformation so we can all sort of understand the angles that I'm sort of asking these research questions. So this is a very idealized sketch of a volcanic system during what we would call a quiet period or a quiescent period. So we have some sort of magma reservoir beneath our volcano. We might have a hydrothermal system above that magma reservoir. And at the surface of the volcano, we can monitor the volcano using GPS sensors to pick up the deformation, seismometers to pick up any sort of seismic energy from volcanic earthquakes. And in some cases, we can measure deformation also using INSAR satellite-based method. So this is our quiescent or quiet period. And then we might go into an unrest period. And we define this unrest period as a deviation away from the background towards a level that might be cause for concern. And that background level and that threshold to moving to unrest is different for different volcanoes, and it's different for the same volcano through time. But we have to go through some change. And that change is decided by the monitoring data that we are using to sort of assess the state of the volcano. So as we flick back and forward, we can see some different changes. And in this sense, some magma has been supplied to the reservoir, and that reservoir has inflated. The inflation of the reservoir also causes the ground to inflate. And we can measure that ground inflation using GPS sensors that are installed on the ground at individual points. And sometimes, like I was saying, we can measure that deformation using satellite-based methods with INSAR. As that magma reservoir swells, we might generate enough stress and strain in the crust to produce small earthquakes, and those are the things we pick up with our seismometer. We can also see that the hydrothermal system might inflate. And that can inflate due to thermal expansion, or it can inflate due to a flux of volatiles or fluids from the reservoir into the hydrothermal system and causing that hydrothermal system to swell as well. And that can cause or contribute to the inflation. So you can sometimes have difficulty deciding between the cause. So for our volcano deformation, we need some sort of source in some sort of medium. So that source could be the magma system or the hydrothermal system. And in the case of what we're studying, the medium is just the Earth's crust. So some source and some medium produces some deformation. In many volcanic places, we also need to consider topography. And what that does is it changes the shape of the medium, and it changes, therefore, the shape of the surface deformation that we would see at the surface. That's not the only thing we need to think about, though. So the spatial and temporal pattern of the deformation, so that's how the pattern of deformation changes with space and also changes through time, is a function of what's happening in our source that's providing the force, and also on the properties of the rock between the source and the surface. And that response of the rock is dependent on the mechanical properties of that rock. So that's things like the Young's modulus or the Poisson's ratio. So if we change the mechanical properties of the rock between the source and the surface, we change the deformation that we record at the surface. So if we flick back and forward here, we can see that we've got some change in our medium, changing those mechanical properties and changing our deformation at the surface. And obviously this is all just schematic, not to scale. But this could be some sort of solidified old sill or some old pluton that's more stiff than the rest of the country rock, and therefore we get less deformation at the surface. It could also be the opposite. There could be regions that are softer than the rest of the rock around, and then we might get enhanced deformation. But the two things to really take away so far is that any sort of heterogeneity in the mechanical properties in the subsurface will change the way that stress and strain is partitioned through the crust, and therefore how that deformation manifests itself at the surface. And that topography can cause extra variations in the surface displacement. And what you can actually get if you have really extreme topographical variations, so like cliffs or sector collapses, you can actually get complete reversals of the surface deformation gradients, which can really complicate how we interpret surface deformation from a monitoring sense. So keep those two things in mind, because they're going to be sort of an almost recurring theme as we go through some of these other aspects of the talk. And I've said I'll be focusing on Soufrière Hills Volcano. It's a dome-building volcano on the island of Montserrat in the Caribbean, and I was just traveling back from there this time last week. It's a beautiful place, but it has also been decimated by the eruption of this volcano. So the eruption, or the eruptive episode, started in 1995, and technically that eruptive episode is ongoing. And this is what they refer to as the megaplot. I didn't come up with that name, but the megaplot because it's sort of trying to crush a load of monitoring data into a single figure. So the top panel is showing the seismicity and earthquakes per day. The second panel is about deformation, and this third panel at the bottom is the gas flux, sulfur dioxide tons per day. And the color bars represent periods of active lava extrusion in the pink, so periods of eruption, and in between these green periods are these periods of unrest between the eruptions. So it's been through their sort of circular pattern of dome growth and collapse and explosions, and then the extrusion stops. And it's shown really nicely by this deformation pattern. So if you follow this sort of red line in the middle panel, you can see that during unrest, magma is still being supplied to the system, the reservoir is inflating, and the volcano is inflating. So we have an uptick in the deformation. And then as the volcano starts to erupt again, and that magma is squeezed out, the volcano and the island start to deflate. And it follows pretty nicely this pattern in the magma extrusion. The big difference now is that we're in this really long period of unrest at the volcano. So the last time anything came out of the volcano was in 2010. And we've got this now 14-year period of continued unrest, but with no surface eruptive activity. And the observatory obviously very keen to understand what's happening during this period. Is it going to be different to these previous periods? Is this the end of the eruptive episode? And these sorts of questions are really important because the southern part of the island is still a complete exclusion zone. So the locals can't go in and reoccupy that area. And there are still houses that are left uninhabited. Well, they're kind of being reclaimed by the jungle at this point. But there's a big social economic push to try and reoccupy that southern part of the island if they can. But obviously there's the hazard associated with that if this is interpreted as intra-eruptive unrest, i.e. unrest that may lead to a resumption of a more eruptive activity. But what we're going to be focusing on is this deformation during this period from 2010 onwards. And these are those data, the deformation data in more detail. So this is just now from 2010 through to 2018. The left panel is showing east-west deformation. This is north-south in the middle and vertical on the right. And each colored line reflects a different GPS station on the island. And I'll show you those on a map in a second. But the main thing here is that the deformation has been continuing from 2010 through to present, if we were to extend this and update the plot. And the rates of those deformation are potentially starting to slow down. So you can potentially see in some of these plots how they're sort of starting to level off a little bit. There's a rate decreasing deformation. And previous work that I'm not going to talk about today shows that this sort of inflation from 2010 onwards can only be explained through continued pressurization in the magmatic system. We can't explain it through some sort of crustal relaxation process or other sort of non-pressurized magmatic system, which may indicate that there could be resumption of some sort of eruptive activity, maybe. So this is the temporal evolution of the deformation. These 4 panels show the same data, but collapsing it down to the spatial pattern of deformation. So all we've done, if we take, I can just reach the top of this black line. So if we take the amount of deformation between here and here, that'll give us a single value. And that's what we plot on these graphs here. And the map on the left is showing the locations of those GPS sites. The red circles are continuous GPS sites, so they record daily, whereas these blue stations and these blue dots are showing campaign sites. So that's where the GPS station is only occupied for a few months at a time, then it's packed up, moved to somewhere else, and then it's reoccupied. So we get this periodic data at these stations. The upshot is still the same. The volcano is inflating from 2010 onwards, but there's some interesting subtleties in here. So the vent is shown by the pink triangle, and the sort of inferred deformation source so far, or at least the surface projection of it, is shown by this purple circle. And if you were to expect a traditional deformation pattern, you would expect the greatest deformation to be closest to the deformation source. But if we look at the vertical displacement with respect to distance to the vent, or the vertical displacement with respect to distance to the source, we actually see that closer to the source or closer to the vent, which are more or less the same, the vertical deformation is actually not the greatest. So there's potentially something happening for some of these closer stations that forces the deformation of this island to not fit the pattern that we would tend to expect. And that also might be something to keep in mind as we move forward. So these are the same data again. As you can probably imagine, I like this data set, so I show it in as many different ways as possible. So on the left, it's the horizontal vectors of deformation, so taking the north, south, and the east, west, and just creating a vector for each GPS station. And on the right is the vertical, and the length of the arrow shows the amplitude of the signal, and the circle shows the uncertainty. But as you can see, the island itself isn't very big. It's only about 6 kilometers wide, and the distance from the vent to the top station there is around 12 kilometers. So it's a very small island, and that very drastically limits the geographical extent of the GPS network. We can't put GPS stations, unfortunately, in the sea. So that is a limitation on how we can monitor this volcano. The other thing that limits how we can monitor volcanoes using GPS is that while these GPS stations are really good at giving us a vertical, a north-south, and an east-west component of deformation, they can only tell us those for the discrete locations where the stations are employed. We have no idea about the deformation in here and in between all of these sites. So it's potentially, we are missing important information. And I've presented this before, and I've had people being like, just use INSAR, like the satellite method. It doesn't work on this island. It's very steep topography, and the whole island is essentially, well, maybe not down here where it's covered in ash, but the rest of the island is jungle. So INSAR doesn't give us a very coherent signal, so we can't use INSAR. So in this first little study I'm talking about, what we wanted to do was try to use an understanding of the mathematical system and numerical models to see if we could identify particular areas on the island that have a higher idealized or suggested deformation signal. And if we could do that, then think about what were the key controls that were forcing those areas of higher or lower deformation signal intensity. So to go about that, we set up a whole suite of numerical models using finite element techniques using COMSOL. So this is what our 3D model looks like. And I'm going to skip over the majority of the details, but I can happily talk to anyone about those later if you want to come for a beer. So on the top of the model, we have the topography and also the bathymetry. Before I was mentioning how that can be important. In the crust of our model, we have the mechanical properties dictated by a 3D seismic velocity tomography. So we can use the VP values and convert them to mechanical properties. And we can load those into our model. And then to drive the deformation, we need some sort of deformation source. So that is shown here. This deformation source is kind of like a rugby ball on its point, and then it's been squished in a bit, so kind of moving towards something potentially more cigar-shaped, somewhere in between the cigar and the rugby ball. I didn't just make that up. That is from like 20 years of people working on the deformation before me and optimizing the sort of deformation source geometry. But obviously, there's uncertainty in that deformation source geometry and its location. So what we did was took the uncertainty in the X, Y, and Z locations, so longitude, latitude, and depth, and also the axes, the A, B, and T axes of this ellipsoid. And we varied the deformation source location within all of that uncertainty, within a three-dimensional grid of source locations. And then we were able to sum and total the deformation from that sort of sensitivity analysis to create heat maps of deformation. And we're going to see a whole series of those in a minute. So here's our first sort of deformation heat map, where the colors moving from cold to warmer are indicating a greater likelihood of suggested deformation. These purple circles are showing the surface projection of our deformation source locations, so varying in this three-dimensional grid. And this is for the vertical deformation only at this point. And immediately we can see for this setup that the vertical deformation, or the highest expected vertical deformation, is not directly around the source, it's off to the east. And that's because of the influence of topography. Got the contours on here. You can imagine this is like a nice volcano. So this area down here on the coastline is easier to deform because it's that bit closer to the deformation source. So that's why we get our peak vertical deformation over here. We didn't only use our sort of semi-sophisticated numerical models. There are other ways to model deformation. So you can also model volcano deformation using analytical techniques. And in those analytical models, you have no topography and you have a completely homogeneous crust. So we did that as well with the same deformation source characteristics and uncertainty. And this is the result you get from an analytical model, referred to in this sense as a Yang model, Yang being the author who came up with the analytical solutions. And you can see it looks very different to the results of our numerical model with topography and heterogeneity as we flick back and forward. For the analytical model, it would suggest that the peak vertical deformation is directly above our deformation source locations and imperfectly concentric as it moves away with distance. So there's no topographical influence there whatsoever. And we can look at the same sort of heat maps for the other components of deformation. So we've got north, south, east, and west. And the really sort of illuminating thing we found here is that peak horizontal deformation is almost always offshore. So down here, always offshore. So if you're the Montserrat Volcano Observatory and you're trying to monitor this volcano, you're never really going to be picking up the peak deformation signal, unless someone's got a load of money to give them to install some sort of seabed sensors. They don't, unfortunately. And again, this is recording the influence of topography. So, and also bathymetry, particularly here for this south deformation component. It sort of bends around the shelf that goes off into the sea. And likewise up here for the north deformation, we do get some sort of higher amplitude deformation on the island. For example, this TRNT station. And in fact, if I flick backwards to here, TRNT is the black line is here, and that does match our highest amplitude north deformation. So we have this sort of consistency between the data and what our model is suggesting, which is ideal. But you can see quite nicely how it's bending around the topography of the island around this area here known as Center Hills, which is the previously active volcanic center. And likewise over here again, it's bending around the Soufrière Hills Volcanic Center. We can compare again between the numerical model and the analytical model. And it's very clear, at least to my eye, and hopefully you guys believe me, that topography having quite a strong influence on changing the shape of that deformation pattern. Although the sort of same broad pattern exists whereby the peak horizontal is still all offshore. We didn't only do this analytical model at one end of the spectrum and our numerical model at the other. We also did the sort of intermediate steps. So we had a homogeneous subsurface with topography and a heterogeneous subsurface with no topography, as well as the full one. And if we explore across all 4 suites of models, it's always topography that's giving us our sort of key control on that spatial deformation pattern. And this is what they look like if you compare them side by side, just highlighting again the role of topography. So now, sort of taking it that step further, we can combine all 5 components of deformation into a single sort of aggregated total as a sort of to give a sort of overview of what we're trying to think we can see. So this is for the numerical model again, with the sort of the highest sophistication. And it shows that where we would tend to expect the highest total surface deformation signal, and these might be where we would suggest that would be best positioned to install a GPS sensor. They're going to pick up ideally the best signal, or the highest signal to noise ratio. But you could only possibly suggest this because if we look at this plot, it would say, all right, so maybe we should install a station here. But this is the top of Center Hills, a highly vegetated, jungled, old volcanic center with literally no access whatsoever. So it's not just our sort of theoretical distribution of where we suggest the greatest deformation. Yeah, just stick a GPS sensor there. It's about access and telemetry and everything as well. But I think the process shows us quite nicely where we could consider in the future. And it matches very nicely with some of these stations are the sort of pet favorites when we were looking at the data before we started this study. They always gave us the best signal. Down along the south coast could be some high potential. Some people have been advocating for them to install a road. So I guess into context, the previous capital here, Plymouth, is completely obliterated, but there are sand miners taking out the ash onto the jetty here and taking it away by boat. They're allowed day access to the exclusion zone. And if you were to extend the road they use around the south, then you might be able to get a sort of quick access. And so there's potential to maybe extend around here in the future. We'll see. Here's that comparison again, just a completion between the numerical results and the analytical results. So there are some subtle differences, again, because of that topography. Okay, so that was the first little study I wanted to talk about. The take-home messages there being that we could start to use numerical models to help optimize or better design GPS networks. We were able to identify some areas that have a higher potential signal-to-noise ratio. And for Soufrière Hills in particular, topography playing the greatest control on that signal-to-noise ratio. That could be different for other volcanoes, of course. But obviously there's limitations, and we can definitely try to do better than that. So now I'm going to be talking about some work done by Jasmine Dibben. She was doing this as her 4th-year undergraduate research project. So only working on it for a short period of time, but she came up with some really interesting results. And what she was trying to do was, instead of using this sort of idealized prolate ellipsoid rugby ball type shape deformation source, she wanted to use the results of seismic tomography as a sort of way to define the geometry of her deformation source. So this shows the results of the most recent VP 3D tomography model for Soufrière Hills. So Soufrière Hills being here, and this sort of low VP anomaly was inferred to be the magma reservoir with a roughly 400 meter per second velocity anomaly. One of the limitations being that the VP anomaly sort of tomography only goes to around 8 kilometers below sea level. But what Jasmine was able to do was to take that full tomography model and clip it at different velocity anomaly levels to extract that sort of geometry of what could be a magma reservoir. And she did that for 2 different velocity contrasts, minus 400 meters per second and minus 450 meters per second. They weren't picked at random. They were extracted from the original tomography paper, who used thermal models that I don't entirely understand. But essentially, they were looking at where they would think for that volume and for the assumed melt sort of content, where it would cross the liquidus, yada, yada, yada. Came up with these 2 values. We used those. Don't ask me any more about them, please. So we had these 2 velocity anomalies, and Jasmine was using these in her deformation models and comparing them to the ellipsoid that I was using previously. She got so far and then she was like, you know what, maybe I should do some hybrids as well. So that's where these guys came in. So in this four here, she was sort of taking the top surface from the seismic tomography and then sort of blending the bottom into something that was more like the ellipsoid, the rugby ball used previously. The reason for that being was because, as I was saying, the tomography only really went down to around 8 kilometers. So this is what happens if you just let the clipping of the tomography do its thing within the uncertainty in that tomography model, and it does close off the geometry. So yeah, to explore that uncertainty and to sort of bridge the gap to that prolate ellipsoid rugby ball type thing, she came up with these hybrids where we just extend the geometry down with depth. So all 6 of these geometries and the ellipsoid were tested in deformation models and sort of tried to evaluate the better fit for the geometry to the observed deformation. I like to call this one the Nemo model because it looks a lot like a fish. So if you hear me say Nemo, this is the one I'm talking about. And if we collapse it all down, we can represent the gross results on these 4 plots. So on the x-axis here is the pressure that's applied to that geometry. So this is the overpressure. And on the y-axis is this J value, and the J value is representing a weighted misfit to the observed data. So it takes all the GPS stations and all 3 components at each GPS station and looks at the difference between the observed deformation and the simulated deformation and calculates this weighted misfit according to the uncertainty in the observation. So from all this, the model runs that Jasmine did, and all the effort she went to extracting this seismically derived reservoir geometry, the ellipse is still the best fit to the data overall when looking at all the data and all the stations and all the components. It has the lowest J value. For the seismic reservoirs, minus 450 meters per second always performs better than the minus 400 meters per second. And of all of these seismic reservoirs, the one that does best is the minus 450 meters per second hybrid extruded, which is this one. It's not entirely that straightforward though. I mean, it could be if we just left it there. But what Jasmine also did is, instead of just relying on this sort of single J value, which collapses a lot of data into a single number, she looked at the difference between the observed deformation and the simulated deformation for all the different geometries and all the different stations and all the different components. And what she found is that some geometries fit some sites better than others. And this is what's kind of shown in these 2 plots. So they're all the horizontal deformation vectors. On the left side here, the black arrow is the observed deformation. The blue arrow is the deformation from the ellipsoid, the rugby ball type thing. And the pink and the purple, which often overlap, are from the Nemo model and the minus 400, the seismic models. Oops. On the right-hand side are the hybrid models. So we've got where they've been extruded or extruded and tapered. And I'm not going to try to explain every single one, but essentially the ellipsoid, because it's been through so much optimization in the past, does really well at fitting the sites that have the least uncertainty. So that's why it performs so well in that J value analysis. Whereas some of the seismic reservoirs do really well at fitting some of the other stations, particularly in the far north and also in the northwest side. So there's a lot of, you can go into the subtleties there, but still the take home being that while we can fit the data with this seismic derived reservoir, the fits do still need some improvement, and the ellipsoid shape still overall fits the best if you take that sort of gross J value. But this sort of hybrid model could be a really cool and neat route forward to explore in more detail, more than Jasmine at least could do with her master's project. But we're still missing something from these models, fairly big one, the magma, right? So previously, all the models I've been talking about so far have been using the approach shown here on the left, whereby regardless of the shape of our geometry, it is included in the model as an empty cavity, and we apply a pressure to that cavity, kind of like a balloon, essentially. So this is simple, it's quick, but it's unrealistic, and it has sort of limited application potential because it's not taking into account any sort of magma dynamics. So what we're doing now is moving away from this sort of approach and towards an approach whereby we can approximate our magma reservoir as more of a mush. We can treat it as a poroelastic medium. So we have a crystal network, and within that crystal network, we can define the porosity of that network and therefore its permeability. And we can actually inject a fluid melt into our poroelastic domain and generate a pressure or volume change in our mush that drives the deformation at the surface. So moving away from this cavity with only solid mechanics to coupling our fluid and solid mechanics together and capturing some of the more sort of realistic, likely mush scenarios we might be seeing. And it doesn't have to have this sort of feeder conduit that's just on there for sort of artistic purposes. So the guy who's been leading the majority of this model development is Rami Al-Shambari. This is collapsing two of his papers onto a single slide. So I want to skip across to the application to Soufrière Hills. But this is what the model looks like in sort of model speak, similar to before. The main difference being that we have this sort of poroelastic reservoir, and we can change the shape and the size of that. We can change the porosity and the permeability using as many constraints as possible. The big difference being when you move to this sort of poroelastic setup is that you add an additional time-dependent component to the deformation. And that's shown quite nicely in this plot here. So on the x-axis is time, on the y-axis is our deformation. It's normalized to this black value. So in this scenario, we're injecting melt from 0 to 2 years, and then we're allowing the reservoir to evolve afterwards. And what you can see, if we focus on the dashed black line, is that after the injection of magma stops, we still get this continued time-dependent deformation. The reason for that is because when we're injecting melt, try and do it this way, the melt percolates through the reservoir, driven by this inlet. And even when we shut off the inlet, there's continued melt diffusion from the high pressure region to the low pressure region. So melt continues to diffuse through the mush and drive deformation at the surface at a rate decreasing step. The same is true if we try to simulate magma leaving the reservoir. So if we take magma out the top, we see subsidence during the evacuation of magma from the reservoir, and then after the magma evacuation or the eruption stops, we continue to see melt diffusing up through the reservoir towards the outlet and driving post-eruptive deformation too. And that's the case whether we have an elastic crust around it, or if you know about these sort of things, a viscoelastic crust as well. So we can couple in the role of temperature, and that's what's being shown with this sort of yellow through to red plots here, showing how this might change as the crust gets hotter or colder. But the main thing here is that we get post-injection or post-eruptive additional time-dependent deformation. So Rami wanted and did apply his models to Soufrière Hills. So the geometry and the model setup visually looks very similar. The difference being now is that our prolate ellipsoid rugby ball reservoir is a mush, and we can inject a melt into that mush. So if I skip through to the results, and this went through like a multi-stage inversion optimization sequence, which I'm not going to touch on at all, but he was solving for the flux of magma, the permeability of the reservoir, and also the depth of the injection point into the reservoir. And if we look at the deformation across this 2010, and this was up to 2022, we had the data for at this point, we can explain it with, if we use a constant flux of about 1 meter cube per second over that 12-year period. And that's for an injection depth, optimal injection depth of around 16.5 kilometers. If we look at the fit between the data observations are shown with the red arrows, the model is shown with the blue arrows. And on the left is vertical, on the right is the horizontal again. The fit between the data and the model is better for stations that are further away from the volcano. And that is potentially due to what I was mentioning at the start of the talk, in that the stations close to the vent or close to the source, the observations there don't really fit what we would expect from a typical volcano deformation pattern. So what we're probably missing is some sort of near surface or very shallow process within the volcanic edifice that is influencing the deformation signals in those GPS sites closest to the vent. So this could be related to the hydrothermal system. It could be related to a solidified cooling dike that we had feeding those previous eruptions. It has also been suggested that it could be related to mass redistribution. This dome has been growing, collapsing, and redistributing material across the flanks of the volcano. So that's something we're still looking to consider. However, if we only use this constant Q, we explain the spatial deformation pattern, but we don't explain the temporal deformation pattern very well. We don't recreate the observed rate decreasing deformation, which is shown here. So x-axis time, y-axis deformation for 6 different GPS stations. The dots are the observations for 1 per day. And you can see, for example, really nicely that the rate of deformation is decreasing. And if we want to match that temporal deformation pattern as well as the spatial deformation pattern, then we need to change our magma flux with time. So this is why I wanted the whiteboard. Good. Right. So Q is our magma flux and his time. So currently we've been using this, and we can use this 1.1 meter cube per second to calculate the total volume injected over that 12-year period. And what we wanted to then do was to look at, okay, what if we inject the same volume, but we change the rate? So we started to play around with things like this. So the flux can start high and then move to low, but the same total volume is injected over the same period of time. And to best fit our temporal deformation pattern, it turns out we need a linearly decreasing flux from around 1.9 meters cubed per second down to 0.3 meters cubed per second. And that gives us our solid line compared to this dashed line, which is a polynomial fits through the data. So it's fitting some stations much better than others. And this, remember, is only one component of 6 stations. So that's kind of interesting that the magma flux might be decreasing over time. Rami went a step further and thought about how that would continue to develop into the future. So this is our decreasing magma flux with time, the green line. So going from 1.9 to 0.3 in 2022. If we continue along that straight line, then the magma flux hits 0 in, say, summer 2024. That's a bold claim, obviously. There's a lot of uncertainty on that. So we can look at the uncertainty by looking at these red lines. And so these are the fluxes, and the equivalent produced deformation is shown here on the left. So the green line corresponds to our sort of optimal evolution in magma flux, the red line being the uncertainty. So no matter where we sort of stop our magma supply to the reservoir, we continue to see low rate deformation for a continuing number of years. And that's because of that continued diffusion of melt. And we presented this to the Montserrat Volcano Observatory last week while we were there, and had a lot of discussion about, okay, what would this mean for the volcano? What would this mean for the stability of the magma reservoir? Because it is a potentially bold claim to make. And there are obviously some uncertainties still within that. But so the sort of take-home messages from this sort of sub-study is that we have had active melt injection at around 16.5 kilometers depth into our sort of poroelastic mush. But that rate of injection is likely decreasing with time, potentially coming to a halt in the not too distant future. But there are still improvements that could be made to those models to sort of get further robustness on that conclusion. So we didn't look at optimizing the geometry of that deformation source in that poroelastic approach. And one of the main limitations there is that the magma flux that we're injecting is completely uniform and bulk with time. So there's no evolution in its viscosity or compressibility or temperature, with time, temperature, or depth. And that's where a current project comes in. So this is a NERC Pushing the Frontiers project that we got funded. So it started in September last year. And we're going to try and take those models on to the next sort of step. So building on the existing work, some of it I've just explained, some of it is other theoretical approaches I don't have time to mention. But what we're planning on doing is bringing in the role of volatiles into those poroelastic models. So instead of injecting a melt and it just being the same with time, temperature, and pressure, we can actually look at the geochemistry or the starting condition of that melt and allow it to evolve as it decompresses and allow it the compressibility and viscosity to change and see how that may or may not influence the deformation that's produced. And then the other side of the project is looking at the stability of those magma reservoirs, which is kind of motivated by this result. So even if magma supply stops and the deformation slows down, there's still melt potentially moving around in the mush, and obviously melt moving around during injection. So what we want to know is the sort of mechanical stability of that reservoir. And it's quite well known, or at least accepted, that if we have this sort of model set up, there's only a certain value of overpressure that this can mechanically sustain before it fractures. Similar to blowing up a balloon, you blow it up too much, it pops. And that's related to the tensile strength of the rock around it. It's less well known how that would play out in this sort of mush scenario. So what we're planning on doing in the project is looking at how the stress, and more importantly for me at least, is the strain rates in and around the reservoir evolve with time. Because we can now do these sort of dynamic models, and for all sort of material failure, it's rate dependent, not just some static overpressure. So we're going to be thinking about how we can potentially start to fail a mush, and whether it fails at the margins or whether it fails in the middle, looking at where stress, strain, and strain rate accumulates during different injection scenarios. And we'll be applying that again more to Soufrière Hills, but also to Sakurajima volcano in Japan, where I've worked quite a lot in the past. So yeah, that's everything. Thank you.
Very much, James. Anyone have any questions? Well, thank you very much for your talk. I really enjoyed it. Very clearly presented and fascinating as well. I just wondered, I mean, if I remember correctly, but I might be wrong, there is a fault system going through the island, and I think it runs northwest to southeast. And I was wondering whether in your work, you've been able at all to see whether there were any interaction between that fault system and the volcano deformation that you were studying, or whether there isn't, or whether you have any comment?
Yeah, sure. So yeah, the faults, there's a big fault that runs through here, and there are others along the same sort of lineation. Our work so far hasn't included it. Previous researchers have looked at the influence of that potential fault system and the other fault systems, and they've seen that it doesn't affect the deformation, because at some point they thought that maybe the deformation was driven entirely by movement on that fault, but that was quickly ruled out. And then when they were doing that, they were looking at the interplay between the deformation source and the fault system. So currently, in our models, we don't consider it because it's been proven to be sort of fairly unnecessary for the deformation. But for the other side of the project moving forward, where we look at the failure, we need to have an actually really good understanding of the regional and local stress. So that's where we're going to definitely be bringing it back in, because if we start to pressurize the system, we want to look at the stress of how this thing fails, and it's potentially a fault running through the middle of it, then we need to start thinking about that. So it's going to be coming into the sort of next couple of iterations over the next year or so. Yeah, that's a really good question. So if you look at this is the current topography of the island, and this DEM was acquired in I want to say around 2014. So after the last eruption ended, because the previous coastline went more like around here. This is an entirely pyroclastic fan. Here it is too. And the topography of the actual dome area has changed quite a lot as well, with the dome collapses creating these quite big scarps. So we haven't considered any sort of dynamic topography because we've only been looking at this period after the last eruption. If there is a resumption of eruptive activity and it, God forbid, takes out a chunk of the volcano, then yeah, it will change our sort of predictions, for lack of a better word, because you start to change the shape of this topography. Maybe it's better shown with this plot, right? So we can see how the contour, maybe I can see it from here, maybe it's more difficult from where you guys are sat, but there are contours bending around the topography. So if we change the topography, then it's going to change quite drastically, where we suggest higher areas of deformation would occur for sure. But although it would also, I guess, it wouldn't just disappear, that material, it would be shifted somewhere else. So we would also probably be seeing changes depending on where it collapses and where the material goes, for example. But I think the changes would have to be pretty substantial, like sort of sector collapse type things, or like taking away large parts of the dome and accompanying sort of to upper flank, rather than just sort of, there was a hurricane that came through and washed out a bunch of the ash. I don't think that would be enough.
Thanks, great to see. You mentioned at the start about the challenge of unraveling signals from the hydrothermal system from the magma. How does that come into your model? Do you have hydrothermal system in your subsurface, or
not currently? No. So if I skip back to my little cartoon, where is it? So the main way that you distinguish currently is that the assumption that the magma reservoir is deeper than the hydrothermal system, which is often the case. And the depth of your deformation source dictates the width or the spatial surface footprint of your deformation signal. So you can get a first order approximation on the depth of a deformation source from the spatial extent of your deformation signal. And for Montserrat, that tells us that the deformation source is mid-crustal. So we don't bring the hydrothermal system complication in. It would add noise to our model. But like I was saying, if we want to really explain some of these near vent signals, some of these signals that don't match the models, and the data just don't marry up sufficiently well for us to be happy with, then we're going to have to start exploring that interplay of the hydrothermal system as well. And there's literally people on the island this week, a project led through Oxford. John Blundy's looking at the potential for lithium in the brines in the hydrothermal system. So they're going to be hopefully imaging the hydrothermal system, and we'll have an idea of where to put it. David?
That was really just last bit of the discussion. So I guess the topography provides a sort of first order kind of explanation for deformation patterns. If we get the sort of state of the scope of the hydrothermal system, it would be sort of a more second order localized effect.
Yeah. It would be sort of the areas around here, assuming the hydrothermal system is in that region. Yeah.
So you mentioned viscoelasticity in the host. I was just wondering whether, what would be the trade-offs of incorporating a little bit of host rock, viscoelasticity along, for example, Q, the recharge. If you did have a bit of deformation within the host rock, then sure that should slow the deformation rates as well.
So that's all in this paper here, and that's what's being shown here. So these coloured lines are for a poroelastic reservoir in a thermo-viscoelastic crust. So the viscosity of the viscoelastic crust is dictated by the temperature, which is dictated by a hydrothermal gradient, geothermal gradient. I blame Janine and David for putting hydrothermal gradient, a geothermal gradient, and a temperature assumption for the magma.
Yeah.
And that's what this TR is, reservoir temperature. So we change the reservoir temperature, we change our viscosity distribution, our viscoelasticity. all those things considered and looking at combinations of poroelastic reservoir with elastic crust, poroelastic reservoir with thermoviscoelastic crust, poroviscoelastic reservoir with elastic crust, poroviscoelastic reservoir with thermoviscoelastic. I've got it confused already. But all the different combinations, right? The upshot being that accounting for the viscoelasticity and the poroelasticity within the reservoir is a waste of time. It doesn't actually do anything. But the viscoelasticity in the crust, and that's the majority of what's driving this signal, can enhance your deformation with time. So that would drop the Q value ever so slightly. It would drop it down by, I don't know, 20% or something. Can't remember exactly.
It's still a small fraction.
Yeah, it's quite minimal. But there are some interesting interplays in the stress evolution, if you're interested in those sorts of things, where where stresses are trying to relax viscoelasticity viscously, whereas they're still sort of driving melt through the system. But,
If you have the stresses that you must have done, you have the information, I guess, on what the stresses are. So
the regional stresses, or
they're just in your models.
yeah, we can output like we can interrogate this model in any dimension, any cut plane, any stress strain, however like, and we've looked at that, and that's kind of what I was alluding to in, I don't know which one of these papers, we look at how the stress evolves around the reservoir with time, kind of thinking around that sort of failure idea, where peak stresses would be for a given geometry.
Does it also, does it also cover the fracture of the stress for the topography itself in part?
We don't sort of,
Is that too small?
yeah, we don't like define any of that explicitly, but we could look at it. And then we've got I know you probably know Craig McGee, right? Yeah. So that's kind of where his project is going. I'm involved with that as well. Looking at how we can, for force folds and type things above intrusions. Yeah, we're going to be starting to account for it explicitly in the models soon. Yeah, Stanley will be here next week. Talk to Stanley when he comes to visit Janine and pick his brains on that.
Just thinking about the patterns and the faults as well, and stress prediction to be localized, they can provide some explanation for smaller unexplained phenomena.
Yeah, for sure.
Any more questions? No? Well, thanks, James. Well,